and we're talking about surface and subsurface applications. Oh yes, yes, definitely. Oil and gas manufacturer, petrochemical industries, very much so. In fact, there are quite a few industries that utilize pumps. I think it would have been easier if I'd asked the question, name me one industry that doesn't use pumps. I think that would have probably been an easier question to answer. When it comes to pump types, we've got two main classifications. These are rotodynamic pumps, and under that pump type, we've got centrifugal pumps that have mixed flow and axial flow impellers, and these can also come in single stage types, double stage types, and multi-stage types. If we look at the other main pump type, we've got positive displacement pumps, and these come in two main subtypes. That's reciprocating types and rotary types. Now, I want you to think for a moment, could you name me two rotary positive displacement pump types? Rotary types that are positive displacement. Have a think and see if you can name me two types. A monopump, well, that's the manufacturer's name, but I know what you mean. It's a progressive cavity pump. And yes, RF screw pump. Well done, guys. Now, there are other pumps that that we need to take cognizance of, apart from the positive displacement and the rotodynamic. And I'm going to use the term centrifugal for rotodynamic. Centrifugal is a lot easier to say, isn't it? Other pumps that we need to be aware of are electromagnetic pumps, jet pumps, gas lift pumps, and hydraulic ram pumps. Now, when we talked about different types of pumps, there's RF screw pump, and we'll show Charles's mono pump, or the correct name is progressive or progressing cavity pump. But we can see several pump types illustrated here. This is our centrifugal pump. Can you tell me what type of pump this is here? In the bottom right-hand corner of your screen. What type of pump is this? It's a positive displacement one, but what type? Any guesses? You've got no graphics on your screen. Well, there may be a problem with your server there. Yes, Charles, it's a gear pump. Oh, good. Guys, excuse me for 1 second. We've got load shedding here, and my lights have just come back on, and everything that was supposedly switched off, is now switched itself back on again. So please excuse me for 1 moment while I take care of a few things that are on. Shan't be long. And I'm back again. Okay, it's so nice when you can see what you're doing. Yes, Charles, it's a gear pump. That's correct. Now, when I asked you to name a couple of rotary positive displacement pumps, you can see that we've got actually several types here. And when it comes to reciprocating pumps, only really two types. That's plunger and plunger diaphragm pumps. And here's an example of a plunger pump. You can see where the name comes from. Here we've got a rod, which we call a plunger, and that reciprocates back and forth in the casing here. And then we've got two one-way valves. Now, think before you answer this question. I'm going to give you a bit of a help. These parts that I'm pointing to now are the valve seats. So there's a seat here and a seat right here. Now, if my plunger was moving left to right. In other words, I'm actually bringing the plunger back and creating a low pressure in here. What will happen to this ball here? What will happen to the ball if I create a low pressure in here? If I pull this plunger back, create a low pressure in there, what will happen to that ball there, the suction valve? That's right, Charles. It will move up, and this valve here, ball will move down. So this effectively, when the plunger moves left to right, in other words, that's the suction stroke, the discharge valve is closed and the suction valve is open, and that allows liquid into the cavity there that's made by this plunger moving back. And then when the plunger moves forward, the opposite happens. The suction valve closes and the discharge valve opens. This ball lifts up and allows the liquid to be discharged into the system. Now, a diaphragm pump is a variation of a plunger pump, and the one illustrated here is a hydraulic diaphragm pump. We still have a plunger that reciprocates back and forth, but now instead of the plunger being in contact with the pumped liquid, it's in contact with hydraulic oil. So we're not worried about corrosion of the plunger because it's not coming into contact with the pumped fluid. What comes into contact with the pump fluid is a diaphragm, a flexible diaphragm. And the diaphragm is shown in the forward position here. In other words, what's happened is the plunger has pushed forward and we've pushed the liquid out into the system. When this plunger moves back, the diaphragm will flip over into the opposite direction and will allow liquid to fill in the cavity that's left behind there. With this particular type, we've got a pressure relief valve. If someone closes the discharge valve or it gets blocked on the discharge side of the system, we won't damage the diaphragm. What will happen is we pressurize the oil up to the set point of the relief valve, and the relief valve will open and allow the hydraulic oil to go back into its chamber here. So it's got built-in protection. Air-operated diaphragm pumps, those are very popular, and we can see how this works here. Now, it's kind of like a diaphragm plunger pump, isn't it? Except now we've got one plunger and two diaphragms here. So we're shown with the diaphragm here on the left in the forward position and the diaphragm on the right in the back position. So with the way this is shown, this is on the discharge stroke, this is on the inlet stroke. So we use compressed air. That moves the shuttle back and forth, and the shuttle guides the compressed air to either side of the system. So in this case here, the shuttle has guided compressed air to behind this piston. This piston has moved to the left, and we've discharged fluid out through the discharge port there. At the same time, when this moved to the left to discharge, this chamber became, the pressure in this chamber became lowered, and we drew in a fresh charge of liquid into here. Now, when this piston moves across to the right, we'll draw in liquid on the left and we'll discharge on the right. And that's how it does it. For every stroke of this plunger, back and forth, we've got one suction stroke and one discharge stroke. And here is an example of some gear pumps. Oh, hang on, I've got another piece of equipment that just switched on. Can I just stop for a moment? Let me switch it off, please. Thank you. Sorry about that, guys. Everything that's on standby suddenly gets switched on when the power gets switched back on again. But that's load shedding for you. Yeah, we've got an example of a gear pump here. Now, let me ask a quick question here. Take a look at the blue gear here. Now, if my fluid is to move from the bottom of the pump through to the top of the pump, which direction should this gear turn in? Should it turn in the clockwise direction or an anti-clockwise direction? To get fluid through here, up out of the top, should this gear turn clockwise or anti-clockwise? Okay, we've got 2 votes for anti-clockwise, which is wrong. What happens here is this turns clockwise. And as it turns clockwise, the fluid gets trapped between the gear teeth and the casing. And as this rotates, it carries around that little pocket of fluid and discharges it out through the discharge port. Similarly, this one spins in the opposite direction. This one spins clockwise, this one spins anti-clockwise. But they both carry pockets of fluid from the bottom here, from the inlet port, around up through the outlet port, the discharge. Then we've got a variation on that. We've got an internal gear pump. Common sense didn't work. Well, sometimes a little bit of science works. But common sense generally works, Arif. Here we've got an internal gear pump illustrated now. Here's the drive shaft, and this gear will rotate. This gear will rotate. This half-moon shaped section here is actually part of the casing. It doesn't move at all. Now, as this gear rotates, as this gear turns, it carries again a pocket of liquid in here, around, up and out through the discharge. So this gear rotates this outer gear. So it's a gear within a gear. Did you follow that? Okay, good. Oh no, Babaloki, have you just joined us? Okay, you've missed a bit then. You've missed nearly 15 minutes of this. Okay, let me. The outer teeth rotate. Yes, they do, because you've got this gear driving this gear. This is, although it looks like it's sectioned through there, this is one complete gear. So as this gear rotates here, it turns this outer gear with it. So the outer teeth, this gear is rotating, in this case, anti-clockwise, and it rotates the outer gear anti-clockwise. So any fluid that's trapped in here, these pockets here, gets transported and out through the discharge. And if you look at this rotary lobe pump, you'll see this more clearly. As this lobe rotor rotates in a clockwise direction, the liquid gets trapped in here, there it is there, and it gets pushed out from there. Now, what do you think rotary lobe pumps, what kind of liquids do you think rotary lobe pumps handle? What kind of liquids do you think rotary lobe pumps handle? Highly viscous, yes, they handle viscous liquids. Semi-solids, yes. As a matter of fact, when you've got these lobes driven by outer gears, and I'll show you an example of this, where the lobes do not contact each other, you can pump things like strawberries. They don't damage the solids. They're very, very gentle, especially at low speeds. And here's that example I was telling you about. Here's my input shaft. Attached to that is a gear. And what you can't see is another gear inside the casing here that's driving this lobe here. So these lobes do not contact each other. They do not contact each other, which means there's no friction between these two lobes. So if I had the choice of using the non-contacting lobe or the contacting lobe here for a product that didn't have good lubrication properties, which one would I use? I've got a liquid that doesn't have good properties. It's what can I say? It's got a high coefficient of friction. Doesn't have good lubricity. Would I use the contacting type or the non-contacting type for liquids that do not have good lubricating properties? Which one would I use? Contacting or non-contacting? Yeah, guys, you got it. I would use the non-contacting. The non-contacting one is not going to be bothered by a liquid that doesn't have good lubricating properties. I would rather use that than use the one here where I've got contact. Where I've got contact, I've got friction. So I need to use this on liquids that can, to a certain extent, lubricate between the lobes. Well done, guys. Now, another variation here is a rotary vane pump. And it works on exactly the same principle as the previous two, the gear pump and the rotary lobe pump, in that we trap a pocket of liquid in between the vanes and the casing, and we transport that around from suction to discharge. And you can see this even clearer on the flexible rotor pump. Here, the rotors turn, and as they turn, they trap liquid in between the vanes. And as it rotates, it pushes the liquid out through there. Now, flexible impeller pumps are very good for highly abrasive liquids. Let's take a look at this. These are rubber, and we can have our casing made out of a hard material or hard face the material with something like tungsten carbide or ceramic. So we can really handle very abrasive products with this type of pump. And then here is our progressive cavity pump. I think this was the one that someone said it's a monopump. I think it was Charles. Charles said this is a monopump, and this is the pump that he meant. These are very good for handling difficult liquids like pastes, sludges, and greases, very viscous liquids. But it doesn't really like liquids with heavy solids in there, because this rotor is normally made out of some type of steel, and our stator is made out of an elastomer. So again, it works on the principle of trapping a pocket of liquid and then transporting along the length of the rotor out through the discharge. So it comes in here, gets transported along the length of the rotor, and then pops out on the discharge there. And then we've got a special type of pump called a peripheral pump. And you can see the peripheral pump has a lot of vanes here, a lot of vanes. This type of pump is good for applications where low flows and high pressures are required. And then we've got the screw pump. In this case, we've got a spindle. That's the driver. and we've got two driven spindles here. And you can see there's a spiral cut in the spindle there. So again, we're using this principle of feeding the liquid at low pressure, increasing the pressure and discharging. And then we've got peristaltic pumps. Where do we use peristaltic pumps, guys? Can you think of any applications for peristaltic pumps? For light slurries, we can, yes, chemical slurries. Oh, with screw pumps, it depends on the type and the pitch of the screw. It can be up 80 bar, 100 bar. With some of these pumps, they're very, very high pressure. Okay, getting back to my question, where do we see these peristaltic pumps? So I've had one answer, and that's from Charles. He says that we can see these handling slurries, light slurries. When I say light slurries, you have to bear in mind we're normally talking about chemical slurries, not mining slurries. The problem is that the rotor, when the rotor turns, it squeezes this flexible tube. If we had any sizable solids in there, the tube would get damaged. Yes, Charles, we use this in chemical dosing. We use it in chemical dosing, and we also use it in hospitals for blood transfusions. When we do a blood transfusion, or we do dialysis for people with problem kidneys, we use peristaltic pumps.